Welcome to this comprehensive lecture on the geometrical interpretation of partial differential equations. Today, we are going to take abstract mathematical equations and turn them into physical shapes you can actually see and understand. By the end of this video, you will know exactly what a partial differential equation looks like in three-dimensional space and how to interpret its components. To understand what a partial differential equation is, imagine you are hiking on a vast rolling mountain range. The physical shape of this mountain represents the solution to a mathematical problem. Now, imagine a steady wind blowing across the mountain. If this wind always blows perfectly along the slope of the ground, never pushing straight up into the sky or down into the dirt, it is tangent to the mountain. A partial differential equation is simply a mathematical rule that describes this exact scenario. It tells us the direction of the wind at any point and demands that our mountain surface must perfectly align with it. Now that we have our mountain analogy, let us define this mathematically. We start with a surface where the height is given by a function of x and y. To make calculating directions easier, we create a master function that captures the entire shape in three-dimensional space. We do this by taking the height coordinate, z, and subtracting the actual surface formula. By setting this entire expression equal to 0, we create a level surface containing all valid points of our solution. This specific format is crucial for finding perpendicular directions. This brings us to our first key formula. To find the direction pointing straight away from our surface, we use the gradient operator. The gradient calculates the steepest slope and always points perfectly perpendicular to the surface, creating what we call a normal vector. In standard PDE notation, we use the symbol lowercase p for the slope in the x direction and lowercase q for the slope in the y direction. The z component is simply 1. So our normal vector is negative p, negative q, and 1. If the slopes p or q increase, the normal vector tilts further away from the vertical axis. Next, we look at the partial differential equation itself to find our wind direction. A standard first-order quasi-linear equation has coefficients capital P, Q, and R. We group these three functions together to form a new vector, which we call V. This vector represents the wind from our earlier analogy. It acts as a tangent vector that must lie perfectly flat against our solution surface. As the values of P, Q, or R change depending on your location in space, the direction of this tangent wind shifts accordingly. Let us visualize everything we have built so far. Here, you can see our curved solution surface in three-dimensional space. At a specific point on this surface, we have two distinct arrows. The arrow lying flat against the curve is our tangent vector, representing the wind direction dictated by the equation. The arrow pointing straight up and away is our normal vector, like a flagpole standing on the surface. Because one lies flat and the other points straight away, they must form a perfect 90-degree right angle. This geometric fact is the key to solving these equations. Before we prove the general rule, let us see this with a concrete example. We are given the equation 2p plus 3q equals 4. Our goal is to find the tangent and normal vectors and show they are perpendicular. First, we compare our specific equation to the standard template. By matching the terms, we can easily see that capital P is 2, capital Q is 3, and capital R is 4. Grouping these gives us our tangent vector. This means at every point in space, our wind is blowing 2 units forward, 3 units right, and 4 units up. Continuing with our numerical example, we now write down the standard formula for the normal vector, which is always composed of negative p, negative q, and positive 1. To prove these two specific vectors are perpendicular, we calculate their dot product, which must equal exactly 0. We multiply the corresponding components and add them all together. This calculation gives us negative 2p minus 3q plus 4 equals 0. By rearranging this expression, we get exactly the original partial differential equation we started with. This confirms geometrically that our solution surface is indeed perfectly aligned with the given vector field. Now that we have successfully used this geometric property in a specific numerical example, let us formally prove that it holds true for all first-order quasi-linear equations. We want to establish the rigorous mathematical test for our right angle. To do this, we use the dot product operation, which measures exactly how much two vectors align with one another in space. For a normal vector pointing straight away from a surface and a tangent vector lying perfectly flat against it, they must form a perfect 90-degree angle. The dot product of any two perfectly perpendicular vectors is always exactly 0. We set up our proof by substituting our general normal vector components and our general tangent vector components into the standard dot product formula. Continuing our mathematical derivation, we now perform the actual algebraic multiplication of our two vectors. We multiply the first component of the normal vector by the first component of the tangent vector. Then do the exact same for the second components and finally the third components. Adding all these individual products together yields negative capital P times lowercase p minus capital Q times lowercase q plus capital R equals 0. Using basic algebra, we simply move the negative terms to the other side of the equal sign to make them positive. This perfectly reconstructs the original partial differential equation we started with. Hence, we have proven that the equation itself is simply a strict geometric rule forcing the surface to align with the vector field. Now let us examine a slightly more complex problem, where the coefficients are not just plain numbers but variables. We are given the partial differential equation x times p plus y times q equals z. Our strategy remains exactly the same as before. By comparing this specific equation to our standard quasi-linear template, we can extract the variable coefficients. Here, capital P is exactly equal to the x-coordinate, capital Q equals the y-coordinate, and capital R equals the z-coordinate. Grouping these forms our tangent vector field. Notice that unlike the previous example, this vector field is constantly shifting its direction as you move around in space. Continuing with this variable vector, we recognize that the vector x, y, z is very famous in mathematics. It is the position vector, an arrow pointing directly from the origin to our current coordinate. Our geometric rule demands that the normal vector is perpendicular to this position vector. Physically, if a surface is always tangent to rays pointing outward from the origin, the surface must be made of straight lines radiating from the center. Geometrically, any surface formed this way is a cone with its tip at the origin. You might wonder why this geometric perspective is so important. Understanding the geometry of partial differential equations turns abstract algebra into shapes we can visualize and engineer. In real life, this is used extensively in fluid dynamics. The wind from our analogy becomes the actual physical velocity of water flowing around a submarine or air flowing over an airplane wing. The equation ensures the fluid flows smoothly along the physical boundaries. Without this geometric viewpoint, engineers would be stuck blindly crunching numbers without understanding the physical reality of their designs. Let us review the key takeaways from this topic. We learned that a first-order quasi-linear partial differential equation is not just a random string of symbols. It is a strict geometric rule. It defines a tangent vector field that must perfectly align with our solution surface. By defining a normal vector that points away from the surface and a tangent vector extracted from the equation, we can use the dot product to mathematically verify this perpendicular relationship. You now have the tools to visualize these complex equations as shapes in space.